unordered partition is very useful. It is frequently used for cryptography, economics, and biology. We usually use Pn to represent how many ways to partition positive integer n into several natural numbers, allowing repetition, and the sequence is irrelevant. We take 3 as an example. Actually, P3 equals to 3, because there are only 3 types of partitions. Take a simple application as an example, such as a servers. For the case that we have 3 identical servers, how are you supposed to use it? It is a typical integer partition problem. Either we use it 3 servers together or 2 together, but the other can be used by itself, or we use 3 of them separately. After having this kind of problem, let's see who is the first one that found out this problem and its solution. We still need to review back to Euler's age. At that time, many mathematicians loved to keep in touch with Euler. Amongst, there is one Mr. Philip Nord. He wrote once in his mail. He asked Euler, did he ever study on the problem of integer partition? Euler is very smart. He did not know what is general function at that time. He did not have this kind of counting concept, but he gave an answer. He said, the number of solution is the coefficient of x to the power of n in expansion of 1 plus x squared multiplied by 1 plus x squared plus x to the power of 4 and so on until 1 plus x to the power of m and so on. Let's look back. What does Euler's answer mean? He wanted to partition a positive number n into numerous ones, several 2's, and several 3's. Then we first look at for 1 over here. If we use general function, it can say 1 does not exist, or use x to represent it has existed once. X squared represents that 1 appears twice. Therefore, the first item for Euler's answer, which is corresponding to the general function for the occurrence of 1. Towards 2, it is the same. There is a possibility where 2 does not exist, or x squared represents 2 appeared for once, or x to the power of 4 represents 2 appears for twice, and so on. So in the corresponding expansion, the coefficient of x to the power of n simply means n is partitioned into several 1's, several 2's, several m's. How many different ways of partition? Integer partition is a very useful sequence. Actually, the authoritative database OEIS has listed as the number 41 sequence. Actually, OEIS is very related to our combinatorics because OEIS is closely relevant to mathematics sequence. Then, when we talk about permutation, combination, and full permutation, several sequences can get corresponding analysis in OEIS and their latest development. Therefore, if students are interested, can frequently use OEIS to solve and find some problems. Now, let's take a look back regarding this integer partition. We have mentioned that towards Euler's method, it is actually using several polynomial multiplication. The method for looking for coefficient to calculate integer partition. But that year was only 18th century. Euler used this method to calculate P29, which means he managed to calculate how many ways to partition 29. Someone commented that Euler's method is really ingenious, but it is not a very efficient way. After that, some people used some recurrence method and managed to have integer partition for a larger number. But people tend to feel that it is very, very difficult, especially for Euler's method. Where is the bottleneck? Let's look back. In Euler's method, it heavily relies on many polynomial multiplication. You need to know at Euler's age, there is no computer, not even a calculator. Therefore, someone like Euler with a super memory, his computation skill is very strong, and he could not only reach 29. After 200 years later, then only another amazing mathematician, Ramanujan, has managed to push the number to 200. The method that he used was different from Euler's. He used a modeling method, calculate the P200 equal to this. Regarding Ramanujan, we do really want to spend some time to share with all of you. Ramanujan was known as the child of Indian. There is also someone who evaluated him in this way. They said, in the history of mathematics, Ramanujan is a very strict person, even in history of science. Why would they say so? Ramanujan has never been to the university, he never exposed to any proper education, but he used his sixth sense towards mathematics. Independently, he found out about 3,900 mathematical formulas and propositions, and he wrote his thoughts into 3 notebooks. And now these 3 notebooks are regarded as a very interesting book in mathematics. One of the mathematicians was trying to prove on Ramanujan's guess proposed in the year of 1916. Then this mathematician was awarded with field medal in the year of 1973. Ramanujan is very weird. He felt that all his thoughts was gift from God, and he never wrote any proof. He wrote a lot of propositions in his notebook. He felt they are right, but why? He did not wrote any analysis. After years later, until now, then only people realized what he had written on the notebook are all right. Especially in year of 2012, there was one popular American mathematician and his colleague has proven that as Ramanujan was laying dying, he left a miraculous function, and it shows that this function is related with the secret of the black holes. Therefore, we can see that Ramanujan, who is such a miraculous people, he even left us with a lot of unknown problems. Even the American Florida University had opened up a Ramanujan periodic magazine, especially published on the research work about 3 notebooks of his. Therefore, you can imagine that when Ramanujan used the method of modeling to push integer partition to P200, somehow people tend to think that Pn will just be ended here. It was less likely that we'll have larger figure coming out. But now, after we checked on OES, P300 is up there, and even more. Why is it so? Let's imagine what had happened. Because we have computers, we have algorithms. Towards Euler's bottleneck, polynomial multiplication, it is no longer a problem for us. So we can analyze here that if we use computer to handle Euler's integer partition method, how should we do? Then we have to first analyze how to use the computer to realize the multiplication of generating functions. Here gx equal to 1 plus x squared multiplied by 1 plus x squared and so on. But computer cannot do a concurrent multiplication, so multiplication is carried out one by one. First, let's multiply the first 2 polynomial expressions. Actually, it is equivalent to get the convolution of coefficients. Assume coefficients are placed into arrays of fk and gk. After the calculation of its convolution of coefficients, we can get the new polynomial expression, and continually proceed with the next polynomial expression to have the next cumulative multiplication and so on. Then we do not need to use manual calculation, but we have applied the method of computer recursive to get the multiplication result. We had written a program to realize the polynomial multiplication. How big the number you guys would like to partition? Let's pick a small one first, which is Euler's 29. It can be calculated very quickly. What is the maximum value that you think it will manage to be partitioned? Let's see, we can try Ramanujan's 200. That's not a problem. 300. Can it be larger? Let's try 416. It's a big number. Can it even larger? For example, 417. Now we found some problems here. There is an overflow while calculating the coefficients of exponent value of 417. You might feel very weird. How come while a computer is calculating integer partition it stops at 417? Let's analyze it. Actually, the maximum integer can be represented in current computers is only 64 bits. This is a maximum range. If we check the P417 is this big, after a tiny increase, using 417 instead, it has far exceeded the largest range. Therefore, we could see that even though we have a computer now, if we are using the traditional method, the generating function method can only calculate up to P416. So what is a bottleneck here? In fact, we will realize the actual bottleneck depends on how we handle multiplication of big numbers. As long as we manage to guarantee a better representation, we will manage to achieve integer partition for larger numbers. Then everyone will be thinking, what is the largest number that integer partition managed to achieve? We have checked from OES for the latest data announcement. It managed to handle around 10 million of integer partition. This data actually is not easy to get. It does not only require everyone to handle the multiplication and the addition of larger numbers, and at the same time, it requires also some modeling method. Actually, integer partition is still a very active subject. It seems that one of the 10-word unsolved mathematics problems have some relation with it. If you manage to break this problem, you will get $1 million award. Then I would like to ask everyone, after you have tried, what is the largest figure you could partition?